Alright, hello, my name is Sarah Evans. I am a physics major from the University of Dallas, and today I will be talking about using non-standard cosmological models to relieve Hubble tension. So, a brief outline of what to expect. First, I'll give you guys an overview of cosmology, then we'll go into what Cosmo EJS is and why I'm even talking about it. Then we'll talk about the standard cosmological model, also known as the Lambda CDM model. Then we'll transition into why should we even consider other models if this is the standard, concluding with a few non-standard models. So, cosmology overview. Cosmology is the study of the universe on the largest scale. In this, of particular interest is cosmic acceleration. So cosmology as a whole was really advented by Einstein's theory of general relativity. Below is the Einstein field equations. Going back to cosmic acceleration, there needed to be a term to account for the universe expanding, which is why this term was added back in after it had been cut out, and is now included as the cosmological constant. So, Cosmo EJS. Cosmo EJS is a software, publicly available, open source, that allows observational data to be plotted against redshift, and then you're able to use different models to create theoretical trajectories of the universe by manipulating the Hubble constant as well as other parameters particular to the given models that you have chosen to use. So, features of Cosmo EJS are all of these observational data sets. In this presentation, we're going to focus on supernova type Ia and gamma ray bursts, which are really good indicators for late universe Hubble constant data. As we'll also be focusing on growth structure and Hubble parameter. Hubble parameter is particularly interesting because it compares the Friedmann metric, which is our manipulation of Einstein's field equation for the standard cosmological model or other cosmological models over the Hubble constant, which will give us a good idea of the ratio between the two. And this parameter uses both late and early universe data, which is particularly used when we will talk about the Hubble tension. In addition, we have a variety of cosmological models available. We have, of course, the standard model. We have the DGP model, which has been proven many times in literature to not be favorable, as well as what I have added, which is the early dark energy model and the quantum chromodynamic ghost dark energy model. Both of these are exotic dark energy models, which suggest something other than the cosmological constant is responsible for our acceleration. We also have other features, including a chi-square fitting, which we acknowledge is not completely reliable, as our data is not evenly distributed over time, because obviously closer observations are easier to get, easier to use, so it does favor later universe. Alright, so standard cosmological model, Lambda CDM or LCDM. What is this? This model comes directly from Einstein's field equations with that cosmological constant added in, seen here. And we have our Hubble constant, which is our present acceleration rate of the universe, and all of this as a function of redshift. These omegas here are representative of the fractional density of different components of the universe. We have curvature we have dark matter, baryons, and dark energy, all which together create the universe. This is a standard model because it is undoubtedly pretty simple, especially compared to the models that we'll see later. However, there are 3 points of hesitation with this model, which is the whole heart of this talk. The first 2 I won't really go into very much. Third, we'll spend the remainder of this presentation. But for your information, the fine-tuning problem has to do with particle physics. Researchers have suggested that vacuum energy, which is the energy that particle physicists have determined to be present in a vacuum, could directly relate to the missing matter of the universe, that cosmological constant. However, the problem with this is that the vacuum energy that they propose is 120 orders of magnitude greater than our cosmological constant. The other one is the coincidence problem, which researchers are asking, why now do we have matter and dark energy within the same order of magnitude? So through 13 billion years our universe has existed. Lastly, we have Hubble tension, which I'll spend the remainder of this talk exploring. So, Hubble tension. Why should other models be considered? Well, Hubble tension arises from a conflict between the late and early Hubble constant calculations. So the late one is measured largely in part using a distance ladder of standard candles. And based off these distances and their redshifts, we can determine our acceleration rate of the universe. The other way is using the cosmic microwave background, or CMB. The CMB first came up about 400,000 years after the Big Bang, which makes it early universe data. Over the past 10 years, 20 years, there's been a divergence between these two values, so much so within their uncertainties they're no longer equivalent, which is what we call Hubble tension. So I'm proposing non-standard might relieve this tension. Now, why do I say that? Well, CMB is calculated within the context of whatever cosmological model is being used. Because we measure the CMB currently now, we have to somehow backtrack it to the original, which we do using our cosmological model, in this case the standard one. So if this one's wrong, then perhaps the CMB data is wrong because of that. The other 2 ways are examining more late universe as the flawed part, which could be the case of modified gravity models, which we won't really be talking about here, or exotic dark energy models where the cosmological constant is not constant, and so dark energy is changing. So the non-standard models that we explored here were the early dark energy model, which is different as it has this asymptotic early dark energy function, which we have our present dark energy included here and here, and then we have this early dark energy that we subtract from it that makes it a little different than a constant. From this, we are able to see, based off of supernova type A, that the standard cosmological model is most likely more preferred, if anything, just because it's more simple, as these chi-squareds are pretty close and you can't really distinguish the 2 plots. With the growth parameter, the EDE model was preferred. However, we have this little bit of confusion at different age of the universe. And with the Hubble parameter, it's really illuminating that the EDE is a worthy champion, as it is much lower, suggesting maybe there is a direct relation between, there is a way to mitigate tension. Then we have the ghost-dark energy model, which it's a ghost. This one is less favorable, as you can see, based on these chi-squares. That's okay. So looking to the future, Cosmo EGS is publicly available, so just because my research hasn't favored this one or does favor this, doesn't mean you should just take my word for it. You're more than welcome to download this for yourself, and we actually hope you do, and explore cosmology on your own. Any questions?